Hello, Glendale Community College students. We are back to talk about intermolecular forces. There are four types of forces: London dispersion, dipole-dipole, hydrogen bonding, and ion dipole. And we're going to talk about these four in this video. The first one is London dispersion force, or you can abbreviate that LDF. This results from a temporary induced dipole due to the electrons being pushed over to one side. So let me explain that better. In a molecule, we have atoms that have electrons going around everywhere. So in a typical non-polar molecule, the electrons are going around and around and around. Let's say for a moment, the electrons get shoved over towards one side. For a moment, that side's a little bit negative, right? Because the electrons are over there. And the other side is a little bit positive. So just temporarily, for a moment, it looks like the molecule is polar, even though it's really not. It's nonpolar most of the time, but just for a moment, it's going to be polar. That's what we mean by asymmetrical distribution of electrons and the induced dipole. It's not a real dipole. It's a non-polar molecule, but it's going to be polar for just a moment due to the electrons being shoved over to one side for just a moment. So everything basically can experience London dispersion force because everything has electrons. But it's the only type of intermolecular force that non-polar molecules experience. So again, it's temporary, and you see it's the only force in a non-polar molecule. It is the weakest type of intermolecular force also. Notice that the more electrons you have, the stronger the London dispersion force can be. So bigger molecules will have more London force than a little bitty molecule, like hydrogen. H2 doesn't have a lot of London dispersion force because it doesn't have a lot of electrons. Here's kind of a picture showing you what I mean. Here's the London dispersion force. We have two non-polar molecules, and they're coming towards each other in the gas state. Now, for a moment, the electrons, those are the black dots, are kind of shoved over to one side. So that side's a little bit negative with the delta minus. It's a little bit negative because the electrons are on that side. The other side of the molecule is a little bit plus because the electrons are gone. Well, when those molecules are close together, because that side is a little bit positive, it's going to suck the electrons over because they're negative and opposites attract. So in the second molecule, we're also going to be polar for a moment. We're going to be a little bit negative on one side, and the other side will be a little bit positive because of the way those electrons are distributed. But then it goes away, and the molecules go back to being non-polar. So if you look at me for a second, so it's kind of like these two molecules get close and they're polar for a moment and they're attracted and then it goes away. And then we have two molecules get close to each other and they're polar for a moment, but then it goes away. So it's just a temporary attraction, often seen in gases because it's really not strong enough to keep you liquid or solid, although there's some exceptions. Okay, but that's the London dispersion force. Non-polar molecules, and it's temporary. Those are the key words. Non-polar molecules, and it's temporary. All right, moving on to the next strongest force, dipole-dipole force. This, you have to be polar all the time. So a polar covalent molecule. Polar molecules always have a little bit minus side and a little bit positive side all the time. They're permanently polar. So the little bit positive end of one molecule is attracted to the little bit negative end of a second molecule. Again, you have to have at least two molecules to have an intermolecular force. This is stronger than London dispersion force because it's permanent. It's polar all the time, not just temporarily. So this is a stronger force, generally speaking, than London dispersion force. And you see this in gases, but some liquids as well. This is strong enough to hold things in the liquid state. So here's an example of HCl. HCl is polar because H and Cl are two different nonmetal atoms. They're different. Cl is closer to fluorine. So Cl is the one that's a little bit negative. The hydrogen's a little bit positive, and it's that way all the time. It's polar all the time. So when a second HCl comes up to it, the H of the second molecule will orient towards the Cl of the first molecule because opposites attract. You won't get two Cl's coming together, right? Because they're both negative. You can't push negatives together. So the Cl's won't come together. The H's won't come together because you can't push positives together. But a Cl and an H will come together. Opposites attract. So they'll get close to each other because they're attracting. The opposite charges are attracting. And that's always there. And it's the dipole-dipole force. Dipole-dipole, yes, you have to say the word twice because we have something with polar and something else that's polar. So dipole-dipole force. That's our second force, and it's always polar, and it's a little bit stronger than London dispersion. Next force, hydrogen bonding force. It's a force. It's not a bond. It's a misnomer. It's not a bond. Sometimes it's called hydrogen bridging force, but we're going with hydrogen bonding force. Okay, this forms between an O or N or F atom on one molecule, and they typically have lone pairs on them, and an H atom that is bonded to an O or N or F on a neighboring molecule. Again, you have to have at least two molecules to have a force. So the hydrogen is a little bit positive in this case because the N or O or F are closer to fluorine, so they're a little bit negative. So the hydrogen on one molecule is going to be attracted to the N or O or F on the second molecule because they have a negative charge and the hydrogen's a little bit positive. So this is stronger than dipole-dipole forces. It's about 10 times stronger. These are polar molecules, yes, but the H to N or O or F bond is exceedingly polar. So it's like superpolar bond. So that makes it a little bit stronger than your typical dipole-dipole force. So here's a picture of two water molecules. Again, you have to have an H bonded to an N or O or F in the molecule to do this. Water has an H bonded to an O. All right, so we have our two water molecules, HOH and HOH. Now again, opposites attract. So the oxygen in the first molecule is attracted to the hydrogen in the second molecule. Again, two O's won't come together because they're negative. Two H's won't come together because they're positive. Instead, you're going to have an H and an O come together. Opposites attract. Opposites. Okay, so it's going to be the hydrogen on the second molecule, which is a little bit positive, is going to attract to that oxygen on the first molecule. And that is the hydrogen bonding force. It's a force. It's an intermolecular force as seen in the red line. The red dashed line is the intermolecular force. Here's another even better picture of the hydrogen bonding force. Notice in this picture, it's always a red oxygen to a white hydrogen, a red oxygen to a white hydrogen, a red oxygen to a white hydrogen, a red oxygen to a white hydrogen. Okay, because opposites attract. It's never O to O, it's never H to H, it's always O to H. Opposites attract. So again, we have several water molecules in this picture, and we can see the dashed lines are the hydrogen bonding forces. Again, they're forces, not bonds, forces. This is an intermolecular force. All right, very good. The last one is the ion dipole force. This is between a polar molecule and an ion, which is just an atom with a charge. So we have polar molecules, again, mean we have a little bit plus and a little bit minus sides of the molecule. And we have charged ions. So the little bit positive side of a molecule would be attracted to a negatively charged ion, an anion, right? Because opposites attract. Or we can have a little bit minus side on a polar molecule would be attracted to a positively charged ion, a cation. Again, opposites attract. So here's a great picture of water and how it interacts with salt, NaCl. On the left side, we see a water molecule. The oxygen's a little bit negative, the hydrogen's a little bit positive. Sodium is a +1, so the sodium is going to be attracted to the oxygen because opposites attract. Now on the left side, we see another water molecule. The oxygen's a little bit negative, the hydrogen's a little bit positive. Here's the Cl -1 because Cl is a -1 charge and it's attracted to the positive hydrogen. Opposites attract. So this attraction is the ion dipole force, and it's the strongest force, by the way. Here's a really good picture of salt water again. We can see the sodium ion, which is positively charged, +1, is surrounded by all the negative oxygens from the water molecules. All the oxygens are going to point in towards that sodium because opposites attract. So there's several of these ion dipole attractions, and that's what dissolves salt in water. Here's a question for you. Which part of the water molecule would surround the Cl -1 ions? Chlorine is -1. Which part of the water molecule would face into the chlorine? Yes, the hydrogens of the water. All the little delta pluses, the hydrogens would point in. So that's a great place to stop. We've covered our 4 IMFs. See you in the next video. Bye-bye.